And here we go. We're going to write a program to do our left sums, our right sums, our trap sums, and estimate the error for our trap Riemann sum. These are Riemann sums. So let's write a test case so we know an answer ahead of time to test the program, see if it works. And we had some test cases yesterday, I guess, but let's start with this. What if I say I want the curve y equals x squared, y equals x squared. And here's the x-axis, and you didn't do that, did you? There's the x-axis, there's the y-axis, there's the origin. And let's say I want the area from 0 to 5. So 1, 2, 3, 4, 5. And so if I take a height there, what the heck was that? All right, so I'm talking about the area bounded by the curve, the x-axis, from x equals 0 to x equals 5, this area, okay? And I'm going to try and make it as accurate as possible. Last time we were stuck in that we could only do 5, 10, maybe 20 tops rectangles by hand. We're going to write a program to automate this so we can do hundreds and thousands very easily. All right, but first we're going to write a program that does left sum. Here we go. So let's do a left sum. How would this left sum look? Well, here's a height, and here's a height, and here's a height of a rectangle, and here's the height of a rectangle. And it should be uniform, but whatever. So if we're doing left sum, for this space, the left sum is f of 0 is 0. Okay. The left-sided rectangle. The left-sided rectangle here is an underestimate. The left-sided rectangle here is an underestimate. Left-sided rectangle here is an underestimate. And let's make it horizontal. And the left-sided rectangle here is an underestimate. So let's see what that is. Let's see if we can write a program to do this for us. Test the program this way. And then we can let the program go crazy. Okay? So what is your left sum in this case? All right, well, B is 5, A is 0, and N is 5. So delta X is clearly 1. Okay. So this is a base of 1 times a height of 0. This is a base of 1 times a height of, well, X is 1, and the function is X squared, so what's the height? 1, okay. So 1 times 1, of course not drawn to scale, is 1. And this is a base of 1 and a height of 4. Okay, so 1 times 4. And here's a base of 1 and a height of 9, because this is 3, right? Okay. And this is a base of 1 and a height of, so 1 times 16. Okay. Well, look at that. We get the first few perfect squares, don't we? 1, 2, 3, 4. Okay. And that sum would be how much? What'd you get? 30? 35? What? 10, 10, 20, 30. It's 30. All right, so my underestimate for L sum is 30. Can I write a program to do that? Same exact thing. Now think of what you were given. You were given the function, so we'll put that in Y1. That's a precondition before you run the program. And you need to know B and A and N to figure out delta X, the width of each rectangle. And if you know the function, you can get the heights, as many heights as you want. So it's up to you to enter in how many n's. And what we're going to do is going to write a program that samples different values of x, that many values of x. Okay? So let's do so. Where is my program? Hang on. I got to start my program. All right, so my programming device, which is a TID3. There's my TID3. And now, wait a minute. Why is it on? This is a miracle. And if for those of you who were here after class yesterday, none of the keys worked yesterday. It wouldn't turn on. Then when I turned it on, I couldn't click on nothing. Now all of a sudden it's on. Okay, well, don't bite the hand that feeds you. And let's go. Program. New. Look at this. I have an LRTE already. Okay, you can call yours LRTE. I'm going to call mine LRTE2 because I'm starting from scratch. I need a blank page, okay? But you can call it LRTE. L for left sum, R for right sum, T for trap sum, and E for the error in the trap estimate, the overestimate to the error we were talking about before. That's the output of this program. It's going to actually print out 4 numbers every time it runs, okay? L's and R's and T's and E's. That's what it's going to print out. All right. But first, let's write a program that does the L part. That's the easy part. Okay. So let's do new. Create new. Enter. And you're going to call it LRTE. I'm going to call it something different. All right. LRTE 2. We're in alpha mode already, so you don't have to hit alpha. Just hit L. And I hate this keyboard. L R T E. And I'm going to make it 2. Now I got to get out of alpha mode to get the 2. All right, whatever. Okay, so the first thing I want to do is I want to, oh, that's my T85 program. There it is, okay. I want to ask the user for input. Now, do you remember how we did that? We did this with Newton's method? No? Prompt. Now, where would I get that? Do you remember it all? You're not required to know how to program this calculator, but just curious if you remember. Program. Go to program, and now you get a whole menu of commands. Where would I go? I/O for input and output, and you could use a lot of different ways of input. The prompt is probably the easiest way. So, and again, what am I prompting for? What am I asking the user for? A, B, and N. The f of x, I'm going to put that in y1 before I run the program. All right. Okay. So let's prompt the user. I'm just simply going to list them. I'm going to say alpha A, because I'm not in alpha mode, comma, alpha B, comma, and alpha N. Where's N? There it is. Enter. Okay. Now from that, I can figure out, the delta x. Remember what was delta x? The width of each rectangle, or the base of each rectangle. How do you get it? B minus A over N. All right, so I'm gonna calculate that. I'm gonna say quantity, since I have all that information already, alpha B minus alpha A, parentheses, divided by alpha N, and I'm gonna store that somewhere so I can use it. Otherwise that answer just gets lost, it gets printed or whatever it does. And I'm gonna put it in alpha H. It's a delta X, but I'm thinking of it as the height of the trapezoids. Do you know the trapezoid area formula? It's base 1 and base 2, the parallel sides, averaged together, add them up, divide by 2, times the height. The height is the distance between the two bases. So what we were calling the base of the rectangle, that's the height of the trap, right? And when we're showing the heights of the rectangles, those are the bases of the trap. So I'm going to call that an H just for shorthand. On the TID 1, 82, 83, 84, you can only use single lettered variable names, so I'm stuck with H. I can't write DX or something, you know? So there you go, there it is. And what am I going to do with that? I'm going to actually, now that I know the base of each rectangle, I'm going to now get the height of each rectangle. Okay, so how are you going to do this? Well, what I'm really doing, remember that symbol for the integral was a fancy S for sum. We're adding stuff up. It's an accumulator function, this integral thing, right? So I'm going to sum things up. I'm going to have to have something to add on to. So what I'm going to do is I'm going to store 0 in something for the left sum. Let's say alpha L. All right, so alpha L is going to be my accumulator or my summation variable. I'm going to dump stuff in there. I'm going to put the first rectangle area, add it to L. Second rectangle area, add it to that. Third rectangle area, add it to the first two. Fourth rectangle area, add it to the first three. So I need a running sum. That's what my L is. It's a left sum, so I'm calling it L. Okay? Are we okay so far? All right, so what I'm going to do is I'm just going to dump areas into L. I want it to start at 0 so I know that there's nothing in there. That's what that does. Starts at 0. All right. Now I'm going to use a common construct called for loop. And let's see. Go into program. Go into control 4. And what I'm going to do is I'm going to do something n times. What am I going to do? I'm going to generate n rectangle areas, right? So I'm going to figure out one rectangle's area, throw it into L. Figure out another one, throw it into L. Do it the same way every time. So I'm going to make this thing into a loop. So hang on. Here we go. We're going to go for, okay, we need some kind of silly counting variable, a dummy variable. How about alpha I? This is very common. Counts from 1 to n, alpha n, and we're going to count by increments of delta I of 1. All right, so if n is 5, like in the example we had a minute ago, 5 rectangles, I is 1, does stuff. That loop is done, starts over. Add 1, I is 2. Add 1, I is 3, I is 4, I is 5. But then if it goes on again, I is 6 is too big, stops the loop, skips the rest of the loop, goes to the rest of the program. That's how a loop goes. So, right? So I'm going to just keep on adding areas, calculating area of a rectangle, area of a rectangle, area of a rectangle in this looping process. Okay? All right, so you'll see how this works when we actually use it. But that's the construct. Okay, enter. Now, what I need to do is I have to figure out the area of the rectangle. Now, we've done it by hand a million times. How do you get it? It was the delta x times the height, right? So, what was my delta x in here? H. And how am I going to get the height? I have to have an x value. I have to know where the x's are, right? Yeah. All right, so look, I'm going to do this. I'm going to say, take your current value of L, add onto it. Now remember, L starts with 0, right? Add onto it the first area, alpha h times y1. Now the TID 283, that defaults to y1 of the current x value. So I have to figure out what the x value is before this loop starts. I don't have an x value yet, do I? Did I store x anywhere? I'm going to have to do that. But hang on, that's okay. And let's store that as my new value of L. Remember we did the same kind of thing with Newton's method? We took the old value of the Newton's method, plugged it back in, so G plus something or other stored back into G, and again and again and again. So we got a new G and then we updated G. Well, we got a new L and we're updating L. That's all. When this loop is done, I'll print out the L. All right, so what's going to happen is I need another value of x. See, there's something missing here. I'm going to leave the blank there for a minute. Then I'm going to hit program end. Okay? So there's my loop. Okay? This loop goes from 1 to n. It calculates areas, adds them up to onto the L, and updates L. I have to get a value of x in here, and I even have to have a value of x before the loop starts. So I'm missing something here. Go to the very beginning of the for line, right on the F. Second insert enter. I'm missing something. I'm missing an initial value for x, and I'm missing how do you get the next value of x every time you increment or you iterate this loop. So what do you suppose is the first value of x? Every time we did this by hand, what was the first value of x for a left sum? Not, well, does it always have to be 0? What if if a is 0 to 5? Yeah, fine. But what if a is, I don't know, 5 to 10? So the first value of x is what? It's a. It's a. All right, so we got to say that. I'm not assuming that my first value of x has to be 0 all the time. It doesn't have to be. So I want to make this a little bit more general. So I'm going to say alpha a gets stored as x. Now there's no alpha x, just use the variable x. And then down here I have to figure out how do I get the next x so I can do the next area when this loop starts over again. So how far apart were the x's? Where we figured out the heights of each left height was a function value, and f of x and f of x and f of x. The first one was at a. Where's the next one? How far apart are they? X plus h, exactly. Aren't they delta x apart? Isn't that what we called h? Right? So I'm going to take, I've found the area there, and I updated L. I'm done with this calculation for L. I'm going to take the current value of x, I'm going to add on to it alpha h, and store that as my new x. So that x now is the correct x for the next loop to start. This is the correct x for next time. So this loop keeps on repeating and repeating and repeating. Question? No? Who has any experience at all with programming of this sort? Computer science stuff, right? Nobody else that took anything to do with computer science or intro to computer science or algorithms or discrete mathematics or something? A little bit? Yeah? Okay. All right, that's all right. This is not required that you come up with the program. I'm giving you the program. But I want you to understand that it's coming straight from the math that we did. This is not coming out of thin air, okay? And I think if you get used to writing this stuff algorithmically, writing this thing in a programming language, you actually learn it better. You understand the process, okay? All right, so that's the end of that loop. Now, what do I want to do with that? I want to display my L value. All right, so I want to, remember, we had input, right? A, B, and N. We had process. All of this stuff is processing the input. Now we have to output. How do we output, do you remember? Display. All right, so program, I/O, and display is probably the easiest way to go. And what am I displaying? What was I calculating? Program, I/O, and 3. And why did I do that? Because now I'm screwed. Yeah, I'm going to do it again. Program, I/O, 3. There you go. What am I displaying? What did I want an answer for? Where's my answer? L. Exactly. Okay, alpha L. All right, so let's test this thing. Remember, we have a test case. Where the hell's L? There it is. We have a test case. If y1 is x squared, and a is 0, and b is 5, and n is 5, L was 30, right? Okay. And remember, it was an underestimate. So if we increase n, that 30 is going to get bigger and bigger and bigger, getting closer and closer and closer to the right answer. Remember, left sum and right sum converge very slowly. We're actually after getting trap sum to work, but one thing at a time. All right, so let's test this thing. Remember, this is a file that's already stored. Just do second mode is quit. And to run it, go, well, what's the precondition for this program? Before you run it, you must have to set up y1. All right, so go to y1, and it's not that. And it's not that. Okay, so I'm going to put in x squared. I can put whatever function I want here. Okay, remember it has to be a smooth function, continuous and differentiable from a to b. And quit that. I'm not graphing it. What am I doing? Go to program, select LRTE2, and hit enter to compile, or actually to interpret. This is an interpreted language. And, okay, so what do you think the input is? Nah, A wasn't 5. It's the other way around. The other way around, not 5. 0, enter. 5, enter. And 5, right? Wasn't it 5 rectangles? And did you get 30? You did. Now, the magic here is if n gets bigger and bigger and bigger, you're going to get some kind of a convergence to an answer from below, because this is an underestimate, remember, right? So it's going to get bigger and bigger and bigger, slowly approaching the right answer. So if I run this again, what? Go back to the program? Okay. All right, so something's wrong with your program, is it? Yeah. Oh, God. All right, let's go through the program again. Program, edit, LRTE2. All right, so we prompted for A, B, and N, and we calculated H. Then we initialized L to 0, and we initialized the first value of X to A, assuming A doesn't always have to be 0. If I didn't do that, it would assume the first X value is either 0 in program mode, I think, or whatever X value you last used on a graph, which God knows what the hell that is. So you really have to start somewhere, right? You have to set it up. All right, last line? Okay. All right, so then there's the loop. And that's the last line, display on. There's a loop. It does something n times. It goes from I counts from 1 to n in increments of 1. So 1 plus 1 is 2, plus 1 is 3, plus 1 is 4, plus 1 is 5. Until you hit n, it does stuff. Then you go 1 more than n, and it'll stop, skip everything up to the end, go to the next line. And you can have a whole other rest of the, million lines after this if you want. And that's the whole program. Does everyone have all of that? Because this ain't the half of it. Remember, we have to get this to do right sum. We have to get this to do trap sum. We have to get this to do the gross overestimate for the error of trap, which we discussed previously. All right, but look at the magic here. What if I run it again? Just hit enter and it'll run it again. And it's still 0 and 5, but now let's make it, 50. So my underestimate is increasing. Is that what we expected? Yeah. Okay. Let's do it again. Enter, runs it again. 0, 5, and 500. Do you really want to draw 500 left sum rectangles by hand? Much less right sums and traps? Now this is going to take a little while. I should really put like a little counter in here so we can tell where n, how far I has gotten from 0 to n, right? 0 to 500. I'm going to put that in there eventually. But I don't know if I'm going to go get some coffee or order some Domino's, get some pizza. I don't know. Yes, Marie. Because you made a mistake. I answered your question. You want me to fix it? Is that what you want? Is yours an error too? All right, that's fine. All right, let's see the errors. Oh, I live for errors. My job is what I do. Go to. No, it should. This what I'm doing here. I made sure to be independent of 83, 84. Is it ecumenical? I don't know about that. All right. Hang on, YouTube. I'm milling around. I don't see an error there. All right, let's see. Program, LRTE, run, 0, 5, and 5. Error, go to what? That should be a plus sign. X plus H stored in X. So the first arrow should be a plus. All right, who else is stuck? Stuck? Anybody? Stuck? Speak now or forever hold your peace. You're stuck? He's unstucking you? It's good? Oh, you got to set up Y1 before you run the program. We good? Everybody stuck here? Make sure you got this program running. You're going to need it on the test on Thursday. You're unstuck? Okay.
I did the 500.
Okay.
So.
Yeah, that's going to take a while. Well, I got what? What I get? 41.5 something?
Yeah,
Okay.
I messed it up. I forgot to do A stores.
Okay, all right. You got it? Yeah? Okay. So anyone else still stuck? All right, now this is good. Now we're gonna beautify this. We're gonna add some little doohickeys here, some little nice things. Okay. First off, I don't want to have to enter the 0 and the 5 50 times. Why? It's not changing. The only thing that's changing is the n, right? I want it to automatically ask me, do I want another n? Would you like another n, master? Right? That's what I want this thing to do. All right. So. Yeah.
Why? It's just 2 steps. Why make a whole new program?
I'm not doing a whole new program. I'm going to add one little thing to this program so that I don't have to start it up every time that I want to change n and then re-enter the a and the b that are not changing. That's sort of a waste of time. I just want to enter n, get an answer, make this a little more efficient. So,
The A and the B are always going to be the same.
a and b are always going to be, yeah, those x values are not going to change for a given problem, for a given area that you're trying to get, right? Okay. The y1 isn't going to change, the a and b are not going to change, the n is going to change. All right. So I'm going to play with this a little bit. Let's see, program, edit, LRTE2. And I'm going to add a while loop, okay? Okay, here we go. Right after the prompt, right there. Because if n changes, I have to calculate a new h, right? So this is part of what gets repeated, okay? So do here, a second delete is insert, enter, get a blank line. In there, I'm going to put a while loop. Okay, now this is a loop that repeats, iterates, only on certain conditions. It asks a question. All right, while something is true, keep on going. If this thing is not true, stop the whole damn ball of wax. I'm going to put the whole program into this. Stop the whole damn program if this is false. Okay, this is what I want to do. I'm going to say while. So program 5, control function 5. While what? Well, n is not 0. Alpha n, by the way, is n really, do you want n to ever be 0? That means 0 rectangle? That's silly, right? So that's my stop value. That's an n value that makes no sense. I can plug in any n value I want, and it'll calculate that many rectangles. But if I plug in 0, which is silly, it knows to stop. Oh, okay, that's convenient. All right. So while n is not equal to 0, now there's a test menu in here. See second math? Okay, second math is test, and I want not equals 2 and 0. So I can enter any n I feel like, and it'll recalculate this whole thing with a new n. But if I enter 0, it knows to stop the whole ball of wax, right? So how does that work? Well, wait, I have to finish the loop. All of this stuff is in the while loop. Give me another blank line at the bottom. And the idea here is, after it puts the answer, L, I want it to ask me, what's the next n? So what do I have to type here? Prompt. Okay, so program, IO, prompt, alpha, n. Where's the damn n? Okay. Enter, and then I have to end the loop, program 7. That's the end of the while loop. Everything else is in this while loop. So if I plug in now n is 10, it'll redo everything for 10. And then 100, and 1,000, and 1,000,000. And if I'm done, what do I plug in? 0, it stops the whole thing. That's a nice clean exit. Okay? All right, let's see how this thing works. Yeah. You don't need it. It's just nice. It's easier, especially under testing conditions. You don't want to waste time having to rerun it for n is 5, 10, 15, 20, and re-enter A and B, A and B, A and B. Only n is changing.
That line that we had that end, was it?
Okay, go back to the program.
Did you need that while line in order,
The while line goes with the end. I just added one little thing before the while loop restarts. I want it to stop and wait for me to enter the new value of n that I want. Whenever you hit prompt, it stops the program, okay? And waits for you to type in like 5, enter. And then the program continues. And at that point, that's the end of the while loop. It starts back to the top of the while loop. The whole program is now in the loop. You have nested loops. You have a big loop. The whole program is in a big while loop that keeps on recalculating stuff when n changes. But in there, you have a for loop that calculates all the rectangle areas. Do you see the logic? Okay. All right. Alrighty. So, all right. So I don't have to look at this. So let's run this again. Program. Well, I meant to do that. All right. Da, 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 da. Okay. So enter. A is 0, B is 5, n is 5. I get an answer. Okay. Fine. Now n is what? 50. And I get an answer. Okay. N is 500. And I get an answer. Now it's slow, but you get the idea. You don't have to restart the program. You don't have to re-enter A. You don't have to re-enter B. When all you got to do is change n. What's the point of that? All right, and we got 41 point something last time, did we not? Yes, we did. All right, let's say I'm happy with that. I'm going to hit 0, and the program ends cleanly. Okay? All right, now, I'm going to beautify this a little bit more. I'm going to clear screens at the beginning of every edit. I don't like the output of one problem to get mixed with the output of another problem. That gets really confusing sometimes. So I'm going to avoid that right from the get-go. I'm going to clear the screen before the program starts every time. And while I'm at it, I'm going to clear the screen every time the for loop starts up again. When the for loop starts up again, I'm going to make it print out the value of I that it's at. And it's sort of like an hourglass, sort of like a ticker tape. It's going to tell you how far you've gotten. I has to go from 0 to 500, and I'm at 100. Oh, I know, I'm not done, but I'm getting there, you know. All right, so this is just beautification. This is not necessary, but I think you find this useful. Okay, go to Program, go to Edit, go to LRTE2. You have LRTE, I guess. All right, so what I'm going to do is right at the very beginning, right there, second, insert, enter, another blank line. I'm just going to clear the screens. And now I forget where the heck that is. Is that Program IO8? Clear home? Yes, it is. There it is. Okay? That just cleans up the screen before any output comes out. So you know that the output that you're getting has to do with what you're doing right now. It doesn't get mixed up with stuff you did yesterday or 5 minutes ago. That can get really confusing. I'm going to do something like that here too, inside the for loop. Right at the beginning of the for loop, right here. Do second, insert, enter, enter. I need 2 lines. I'm going to do a clear home, Program IO8, and I'm going to do display I so I can see where I is. Program IO display I, so that if this is really, really slow, I have a feel for where I'm at in the problem. I could maybe like go and do something else and come back to this. Okay? So second quit that. Now this just, you know, creature comforts. Okay? Making it easy to use. That's all this is. Where do I put it? Program, edit, what is it, 4. The first clear home is the very first line. And the other clear home is inside the for loop. But what I wanted to do, think about what it's going to do. Every time the for loop starts, it cleans up the screen and prints I. And does stuff. It doesn't display anything until the loop is done. After the loop is done, then it displays L, right? So all it's displaying is clean the screen I, clean the screen I, clear the screen I, clear the screen I. So you're going to see the I counting 2, 3, 4, 5, 6, 7, 8, up to 500 or 5 million or whatever it is. So you get a feel how fast it's going. Because otherwise, sometimes you just sit there like, oh, it's almost done, it's almost done. It's not. And you're wasting your time, you know. So, all right, let's run this version. All right, so I don't even have to clear anything here. If I run the program, it's going to clear the screen right from the get-go, right? Then I'm going to go 0, 5, and 5. Do you see how it counted up there? Then 50. See, now it's counting up to 50, so you know how far it's gotten. Oh, I'm almost done. Okay, I'll wait. Okay? And then 500. All right, now look, see, now you know. Okay, it's going to take a while. I'm going to go do something else. I'm going to do problem 15 on the homework. I'm going to wait for this one later. Or I'm going to do problem 3 on the test. I'm going to leave problem 2 for a minute. You know, I mean, because it's slow. It is. Unless you use ludicrous speed, which we already figured out doesn't work too good on the 83 emulator. But the 89 emulator is actually nice. All right, we're getting there. 300, 330, 340, 350, 360, 370, 380, 390. It's not that slow. All right, it's doing 500 iterations of getting those areas, and boom, there's the answer. I don't know if I really want that 500 sitting there with the answer sitting there. I think I might put a clear screen at the end too, just for fun. Throw in a 0. Give me a 0. Boom, so I can stop. Program. Edit. LRTE -2. I'm going to put a little clear screen at the end, right before it displays the answer, so that the ticker tape, the hourglass, the progress bar. It's like a progress bar, right? It's at this side graph. I'm going to put that, where am I going to put that? I'm going to put a little clear screen right here too. Second, insert, enter a clear home program IO 8, just so that the output doesn't have that 500 or whatever stuck in there. It's not part of the answer. Okay? So let's just test that again. So run it. And then 0 to 5 in, I don't know, 1 rectangle. Wow. Why does that make sense? 1 rectangle, I got 0 area. Why does that make sense? Because the left rectangle, the first one was 0, and I'm only getting 1 big fat rectangle with a height of 0. That's silly. All right, how about we do 10? It's counting. The counter's gone. That's the answer. Okay? How about 100? Okay, counting, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. The counter's gone. There's the answer, and so forth. Okay, now this is nice. I like this. Now I'm going to add to this. Okay, we good? We're beautifying, right? Okay, this is what people do when they program. They end up spending forever tweaking the output, making it look better. Program, yeah. All right, this is basically the whole program, but now I'm going to add to it write sum. I'm going to add to it trap sum, which is actually going to be very easy. And I'm going to add to it trap error and all that stuff. But this is basically the skeleton of the program, okay? So in case you're missing anything, program, edit, 4. All right, so clear the screen just to clean things up. Enter A, B, and N. And then this loop controls asking for new values of N. Yeah. Yeah, if you're on an empty line, all right, let's make an empty line. All right. Say you want to get rid of that line. Just go, is it delete? Delete, yeah, at the beginning of that line. Yeah. Yep. All right, so then that's the beginning of the while loop. All right, what do we do in the while loop? We calculate your delta x every time that n changes. We called it h. We initialize the sum to 0. We initialize the first x value for the left side rectangle for the a value. And then the for loop does all this iterations of finding area, adding it on for different x's. This is just creature comfort. This is not really required, just so you can have like a progress bar. It's not even a bar because it's not graphical. We could get really fancy and graphical with this stuff because it's a graphing calculator, right? Some people go insane with the thing actually drawing the rectangles and shading them in and graphical progress bars. It would take like 3 months for you guys to copy the program. I don't want to do that. All right? I'm trying to keep it simple. Believe it or not. I'm trying to keep it simple, stupid. I am. Okay. Kiss. Don't forget kiss. All right. And then clear the screen of the counter, of the progress bar, put out the answer, ask the user if they want more stuff to do, basically, right? All right. Now, the rest is actually very easy because remember, we've done this a couple of times. What's the difference between the left sum and the right sum? It's the same rectangles in the middle. Remember? You subtract the first rectangle area, it's gone. You're not using that left one, but you're adding on another one on the right. Okay? Now, if it's not always the case that the first x value is 0, so we fix that, we initialize it to A. It's not always the case that the first left rectangle is 0 area either, right? So what if it's non-zero? I got to get rid of it, and then what do I have to add on? The rectangle on the right side, rightmost side, remember? Right? There was always that one rectangle was very big and the one rectangle was very small. We got rid of that and we added the other one. That's what I'm going to do. Okay, so this is what we're going to do. Here we go. Right after the for loop is done. All right, where is that now? Right there, right there. No, that's the end of the while loop. Right after the for loop, right there. Okay? In fact, I could probably do it right here. I'm going to figure out what R is. Let me think. Right, okay. I need 3 lines. Second, delete is insert, enter 3 times. 1, 2, 3. I'm going to figure out my right sum before I can print it out, right? This is my right sum. It's going to be alpha L plus the next rectangle that the loop didn't use, right? Remember, the loop went up to n, right? Say I goes from 1 to n is 5, right? But the I became 6. It actually incremented x to that new value. It didn't use it, right? When I became 6, it already had the right x value for the next rectangle, right? So I already know where the x value is. So I can just say add on, let's see, add on alpha h times y1 at that x value that the loop didn't use. The very last x value that it didn't use is the next rectangle's left side, isn't it? Believe it or not, it is. Okay. Now, I'm going to store that as alpha r. That's my right sum, but not really, because that adds on the big rectangle we were missing. What about the first rectangle? I got to get rid of it, right? Now, where was it? It was at A. See, I don't know, right? I don't know the x value where I'm at right now, but I know where I started. I started at A. So I have to hit enter here and do alpha A gets stored as x again, so that I can now take the right rectangle, alpha r, and fix it. What's wrong with it? I have to subtract alpha h, the base of that rectangle, times y1, the height of the rectangle, at A, because x is now A. You don't have to specify it here. Now, some TI calculators, you actually have to use function mode here, and it's required to put parentheses, x parentheses, right? But here it's not required. And store that as the final value of r. Now, remember the name of this program, LRTE, because it's going to print out L, it's going to print out R, it's going to print out T, and it's going to print out E, right? So, let's finish this program. Let's go to the next line. Right there, right after the display L line, right at the beginning of the prompt line, I need, again, 3 blank lines. Right? Is that all I need? Yes, that's all I need. Okay, ready? 3 blank lines. Here they are. Okay, second, delete is insert. Enter, enter, enter. I'm going to display R. All right, so program IO display alpha R. Okay. And I'm going to display T, yeah? You could, but it's a pain in the ass, the syntax. I don't want to get into that. Yeah, yeah. And in fact, I should, sometimes I actually label it, so it prints out L equals number, R equals, I don't want to get too crazy with the syntax here, so if you want to RTFM and fix up your own program, that's fine. All right, so I figured out L and I figured out R, and I'm displaying them, but I didn't figure out T, did I? How do you get trap? Average L and R. So just display that, L plus R divided by 2. That's it. All right, so display, program, IO, display, quantity, alpha L plus alpha R, close it, divided by 2. That's trap. I don't need it anywhere else, so I'm not going to store it anywhere. I'm just going to display it. Calculate, display it right away. And then I need the E. Now, before we said that the error of trap is overestimated by f of b minus f of a times delta x over 2, right? It can be shown that that's the same thing as L minus R times delta x over 2. So I'm going to display that. Now, sometimes if you have an overestimate or underestimate, the error might be negative. I'm not worried about whether it's negative or not. I'm worried about whether it's how big it is or how small it is. I want it to be small, right? So I'm not really worried about whether it's an over... Well, actually, the sign will tell me if it's an overestimate or under... All right, we'll play with that. But don't worry about the sign right now. If we're subtracting L minus R, it could be negative, right? If R is bigger, it could be, right? So you might have a negative error here, but don't worry about that right now. All right, so here's the error term. Program, I/O, display, boom, quantity, alpha L, where's L? Minus alpha R times alpha H. Remember that was the area of all the errors put together as one big fat rectangle, right? They all had the same delta x, and then you added up all the errors, right? Okay, times alpha H. Whoops, I got rid of the alpha. Whoa. And then, since it's trap error, the error is half as much. Okay, there you go. All right, now this is what you're going to do. You're going to make a convergence table for all of this stuff. You're going to run this for a particular y equals, y1 equals, whatever, right? And for a particular a and b. For different values of n, you're going to see that L converges to something, R converges to something, trap converges to something, and the error goes to 0 or damn close. Okay? And we're going to have to write those results in the table somewhere. That's all, on paper. Okay? All right, so that's what we're going to do. All right, so let's try this out. Second quit. And program. Enter. You can do program, whatever. All right, so 0 to 5 in 5. All right, so my left sum is 30. My right sum is 55. My trap sum is the error, the average. And the error term doesn't mean a damn thing unless it's less than 1. All right, in absolute value, 12.5, that doesn't tell me a damn thing. I want it to be less than 1 so I can see if it's less than 0.005, so the hundredths place is okay. If it's less than 0.0005, so the thousandths place is okay. Sometimes you're going to get answers converging to the thousandths place, or whatever you want, faster looking at the error term, or faster looking at the convergence of trap. So that's why I have both. So it saves you time. One of them will get to the answer quicker than the other sometimes. All right? So we're doing a convergence table for trap, but sometimes we get the answer in the error term quicker, so it's convenient to have it there. All right, so what are we going to do? We're going to write that answer down. Let's see. Let's write that down. All right, so let's make a little table. All righty. Okay, so for different values of n, for different values of n, I'm going to have an L. Wait, how am I going to do this? Am I going to do this way? I'm going to do this way. I'm going to have an L, an R, a T, and an E. So get rid of this. Okay? So when n was 5, here I got 30.0, .0000. This one was 55, wasn't it? 0.000. And where's my calculator? Okay, 42.5. Okay, so 42.5. And might as well write it. It doesn't mean a damn thing unless it's less than 1 in absolute value, but let's write it down. Okay? All right, so now let's do another column. And what we want to do is see how it converges, that's all. All right, so let's do the 50, like we did previously with just L. Let's see how it works with everybody, 50. All right, so it's counting up to 50. For I goes 1 to 50. And now the error is less than 1, so that's starting to tell me stuff. The error is less than 0.1. That's telling me that the trap estimate is good to the units place. The error is less than 0.1. So there's 0 error in the units place. So the answer, the real answer, if you could do this exactly, is 41 point something. I know the 41's good. Even if it doesn't show up that we have convergence with 41 on the trap. Okay? So let's write that down. 40.4250. Okay. 40.4250. And let's see. No, I better not do that. All right. And what was it? 42.925. 41.6750. And this was 0.1250? Stupid pen. I don't know why it's sticking. It never does this at school. All right, so the gross overestimate to the trap error is that this error, whatever this answer is, it's within 1/8 of the right answer. This is an overestimate to the error. If I knew the exact error, I could just add it on to this and get the answer. I can't do that. I don't know that. This is an overestimate to the error, okay? Now notice that this is decreasing, right? So this is an overestimate, this is an overestimate, it's getting smaller and smaller and smaller. So when this is negative, trap is overestimating, I think. If you want positive to be overestimating and negative to be underestimating, that might make sense. You might want to change the error line. Where I wrote L minus R, you might want to write R minus L. I wasn't sure which way I wanted to go. Okay? If you want the negative to mean something, usually a negative error means an underestimate. If you don't care about that, that's okay. You don't really need to know that. This thing was concave up, right? Remember y equals x squared? This thing was concave up. Didn't we say when it was concave up that trap is overestimating? So if it's converging, it's going to converge from above, getting smaller and smaller and smaller, right? This makes sense? So you know it's an overestimate without this telling you. But I like an error to be positive when it's an overestimate and negative when it's an underestimate. I might want to fix that later. Well, don't worry about it. Don't worry about it for now. All right, let's make it 500. All right, now it's time to go out and get some coffee. Go to the water machine. Do some gossip. Go to the coffee machine, get a filter. Get some grinds, clean up the pot. Oh, geez, you know, somebody messed up the pot. All right, brew some coffee. Wait for it, wait for it, wait for it. Pour out the coffee. Look for the Splenda. Where the hell did he put it? Where did they put the Splenda? And, I got my coffee. Come running back. And hey, I got an answer. Hey. Right? This is what the progress bar is about. You know, how much time do you have to play with? All right, so someone have that on their screen so you can tell me what it is. So I don't have to jump back and forth 50 times.
41.
All right, so this one is 41.5418. All right, remember we're doing fixed four, so three-place convergence. Fixed four convergence, so three-place accuracy, right? All right, this one? 0.7918. Pretend that's a 7. And? 0.6668. Ooh, look at that. And what's the error? 0.0013, and it's still negative, I guess, right? And this, I want this to go away. There, okay. All right, now look at this error. Forget the negative for a minute, because negative I usually think is an underestimate. I got this backwards, but take a look at the opposite value. There's no error in the 10th place, no error in the 100th place, and this is not 5 or more. If this were 5 or more, there could be like round-off error. So that's telling me that the trap estimate is perfect to the 100th place. No matter how many n's I do. Right now, n is 500, right? No matter how big n is, the first 4 digits here to the 100th place will not change. All right, it's 41.66, period. End of story, done. All right, at least to the 100th place, that's the exact answer. Not rounding off, that's the exact digit in the 100th place in the full answer. If it's irrational, irrational, whatever, I don't know. Okay? Do you have any idea what that is? 41 and a fraction? It's probably 2/3. 41 and 2/3. Okay? That's what's happening. Okay, and we can run this for 5,000, 5 million, whatever. It's going to take a while, but you get the idea, right? Okay. Now, here's the magic. Here's more magic. Now, you got the program running, right? And you understand what the program is doing? Okay, forget the program for 1 second. This is tomorrow, but I would just want to clue you in on what's happening. That's the graphical numerical approach, getting an estimate to the answer, right? Here's the analytic exact answer. Who knows how to do this exactly? Who knows how to prove that this answer is really exactly 41 2/3? Because that's what you're thinking, right? The 0.66 2/3, right? This is how you do it. The fundamental theorem of calculus says that all these weeks you're finally ready for the fundamental theorem of calculus. Are you ready? The fundamental theorem of calculus says that the numerical integral from a to b of f of t dt is cap f of b minus cap f of a, given that f and big F and little f are continuous and differentiable from a to b, and that cap f prime is little f. Cap f prime is little f. What the hell does that mean? Well, let's see. That's what this is what it means. The integral from 0 to 5 of x squared dx equals, can you think of a cap f, a function, whose derivative is x squared? Now you know derivatives, right? Remember 3 weeks of freaking derivatives. Don't let me down. Now, that's why we did 3 weeks of freaking derivatives. So we can do an antiderivative now. Are you ready? This is the antiderivative. Cap f is the antiderivative of f. The definition of antiderivative is its derivative is the function you want. Okay? So can you figure out a function whose derivative is a function they gave you? What do you think? 3x to the third over 3. Now let's just check his hypothesis. Just x to the third over 3? Okay, like that? Because differentiate this. What do you get if you differentiate x cubed? 3x squared. And what's 3x squared over 3? Yes? Good? Okay, now look what happens. Evaluated from 0 to 5 means plug in 5, that's the b, right? A to b, that's the b. Plug in b into this cap f. So 5 cubed over 3 minus, how do I write cap f of a? This is cap f, the antiderivative of this, little f. I plugged in 5b. Now I want to plug in 0, so what do I write? 0 cubed over 3, which is silly, that's just 0, right? Okay. But what is 5 cubed? 125 over 3. Now how many times does 3 go into 125? And what's the remainder? It can be shown that this has to be the exact answer. No matter how big your n is in the previous convergence table, the answer is always going to give you 41.66666, as many sixes as you want. That's what 2/3 is, right? All right, so that's what we're leading toward. That's tomorrow. I really didn't say that top secret. Don't tell anybody I told you I'd have to shoot you. Yeah? Cap f is the notation I'm using to denote the antiderivative of little f. The thing whose derivative is at little f. That's all the cap f is. Cap f is a function whose derivative is little f. So you're trying to differentiate, you're trying to do derivatives backwards. You're trying to think of what was it that they differentiated so they got x squared. Okay? Now, you know a lot of antiderivatives, don't you? Look. If y is x squared, y prime is 2x, right? So what's the numerical integral from 0 to 1 of 2x dx? It's x squared evaluated from 0 to 1, which is 1 squared minus 0 is 1. Now this you can prove with a triangle. Remember, we could do areas exactly with a triangle? Y equals 2x is a line, right? If you, what are you doing? If you graph that, what do you get? Let's see, let's graph that. Y equals 2x from 0 to 1. From 0 to 1, that's all I'm caring about. From 0 to 1. Now, if you plug in 1 into y equals 2x, you get 2. All right, so 2. So it goes through this point, and it goes through this point, and it's a line. What's the area under this curve? Well, it's a triangle, yes? How do you get the area of a triangle? The base is, the height is 1/2. The base times the height is 1. 1/2, 1 times 2 is 1, right? Okay? So if you can name the antiderivative, you can get an exact analytical answer. This is the analytical or algebraic approach. If you can't name an antiderivative, then this program thing we did and convergence tables is your fallback position to get an estimated answer.
On an exam, will be responsible for both.
Yeah, exactly. Yep. Okay? So yesterday and today we're doing this graphical numerical stuff. Tomorrow we're going to practice the analytical stuff, okay? Whoa. And it's just time for YouTube to go to bed. Good night, YouTube. See ya. Have a nice day.